I'm not the show here. He is.
The dancing comes Wednesday at the room session. That's the dancing.
Anyone interested in randomness, please come in now. Okay, hello everyone. Welcome to the randomness session. The first talk in this session is about fuzzy extractors and their possibility by Benjamin Fuller, Leonid Razin, and Adam Smith, and Ben will give the talk.
Okay, thank you. Thanks everybody for coming. As Dominic said, this is joint work with Leo Razin and Adam Smith. So before I can tell you when fuzzy extractors are possible, I'll tell you a little bit about what they are. So the goal of this talk is to understand when we can get key derivation from noisy sources. So noisy sources are things like physical uncodable functions, biometric data, and so what we're considering is a class of sources of entropy where they have noise in them. So we can take some initial reading from them that we're going to call W0, and this is not equal to a later reading. If we measure the same thing again at a new time, it's going to be a different value, W1. But these two readings aren't going to be independent. We're going to assume that there's a bound on the distance, that the distance between W0 and W1 is less than t. So for most of this talk, we're going to consider the Hamming distance, but you can define this perfectly well for any distance metric. And so what we want to do is get a cryptographically strong and stable output from these readings. So W0 and W1 should map to the same output that should look uniform to the adversary. And if we can do this, we can use it to bootstrap authentication. So a little bit more what this setting looks like is that we have our traditional Alice and Bob. So we have a baby who wants to use Facebook. And so it takes an initial reading, W0, from its biometric data, sends this value over to Facebook. And then at some later time, maybe when it's grown up, it takes some later reading, W1. And now Alice and Bob want to communicate, except now that there's a non-tampering Eve that is observing their communication. And they should, because they have these values W0 and W1, be able to agree on a cryptographic key. So this problem and variants of it have been studied for 40 years, starting with the great work of Weiner and the wiretap channel in 1975. So today we're going to consider the non-interactive setting, so where there's a single message from Alice to Bob. Okay? And in particular, in this setting, we're going to use the notation of fuzzy extractors. So we have an enrollment algorithm that's run by Alice called generate. So it takes this value W0 and produces a cryptographic key R as well as a non-secret value P. And the point of this non-secret value is now we can run reproduce when the distance between W0 and W1 is less than t. We take W1 as well as this public value P to get back our value R. And the correctness condition is that reproduce should give us the same key if W0 and W1 were less than distance t apart. And the security condition is that, well, R should look uniform given this public value if the source is good enough. And what we're going to talk about in this talk is what does good enough mean. So to start, we're going to go to a little bit more familiar setting, which is rather than asking when are fuzzy extractors possible, we're going to ask when are extractors possible. And I hope people in this talk are a little bit more familiar with randomness extractors. So here, we get rid of this distance t, and normally we call this value p a seed. So in the randomness extractors game, we know that an adversary can always try a guess W0 in the distribution. So whatever our source looks like here, they can pick some value and run that in the reproduce algorithm, and they get some candidate key out. So the necessary condition for security is that every possibility W0 has to have low probability. Okay? And so we codify this notion in something called min-entropy. which says that every point in the distribution has low probability. It's necessary for security, and the nice thing about randomness extractors is that it's also sufficient by the leftover hash lemma. We can show that universal hash functions actually work as extractors, although they have some limitations. They have long seed, they have some losses associated with them. So for randomness extractors, we have a really tight and clean condition that's both necessary and sufficient for security. Okay? So now going back to the fuzzy extractor setting, we want to ask, what's the equivalent condition? So what we can do in this setting is that an adversary doesn't have to exactly guess W0. What they have to do is they get to provide an input W1, and they should provide an input W1 that's near many possible values. So what it looks like is they don't have to guess any of these points. They can provide an input point here, and they win the game if the point they provide was close to the actually generated point. So the equivalent condition is that every ball of radius t should have low probability. Little weight of the distribution should reside in any ball. So we're going to define an analogous condition that we call fuzzy min entropy that, like min entropy measures the maximum probability point, this measures the maximum probability ball in the metric space. Okay? So you might ask, why should we bother with this new notion? We can show that fuzzy min entropy is at least min entropy minus the size of the ball. Why don't you just measure things like this? In fact, that's what fuzzy extractors mostly did. Is they talked about your starting entropy, and they had some losses associated with the size of the ball due to losses from coding theory. And so the reason for this is that there's many distributions that occur in practice where the size of this ball is actually greater than your starting entropy, starting min entropy. For example, the human iris has this condition where the t that you need to correct has like 2 to the 200 points. Actually, it has like 2 to the 500 points. And the entropy of the distribution is about 250 bits. So if you measure things this way, it says that the iris is impossible to secure. But this is what the distribution actually looks like. And if you look at that attacker who just provided an input point, this doesn't look too bad because they're not going to capture a lot of W0. So our hope is that this fuzzy min entropy is a much tighter measure of whether a distribution is actually capable of being secured by a fuzzy extractor. Okay. So maybe we actually have this setting where hfuzz is greater than 0. Okay. So an adversary can always try this. So it's pretty easy to show that fuzzy min entropy is in fact necessary for security. So our goal is to say we want to make sure that that's all an adversary can do. And in the computational setting, the answer is yes, using obfuscation. And this is the work of Batansky et al., who showed virtual gray box obfuscation for NC1 circuits. So basically, what you would do is inside of generate, you'd pick a random key R, and this public value would be an obfuscation of a proximity point program. And then in reproduce, you would just send your input to this obfuscated program. And since for most natural distance metrics, you can compute this distance in NC1, the work of Batansky et al. Gives you a VGB obfuscator and thus a fuzzy extractor. And this construction is exactly secure when the distribution has fuzzy min entropy. So that's kind of evidence that we're on the right path. So the question we ask in this talk is, what about information theoretic adversaries? And so what we show is two things. One is we show that this measure is sufficient if the constructing algorithm knows the distribution completely. But we also show something I think is a little bit more interesting, which is if the constructing algorithm only knows the distribution comes from a family of distributions, that this may actually be insufficient. And we have several variants of this impossibility theorem. So this sufficiency theorem is using some universal hashing techniques with a little bit more sophistication. I'm not going to spend much time on it today. What I want to focus on is the insufficiency. Okay? So, right. The reason we want to focus on this case of distributional uncertainty is that's almost always what we're working with. In the randomness extractor setting, you want to provide security for all sources with a certain amount of min entropy. So here we'd like to provide security for all sources with a certain amount of fuzzy min entropy, the same kind of condition as in the extractor setting. There's many reasons why you would want to do this. The first is that if you're constructing an algorithm, you've seen some samples from a high entropy distribution. You don't know the entire thing. So whatever you haven't seen, well, there's a bunch of possible distributions that could fit that. It may be that Eve knows more about your distribution than you do, right? Once you come up with a construction, they can spend more time and money to learn how the iris works, to build an underlying model for it. And the third thing is that you can't hope to have a computationally efficient construction if you have to record all 2 to the 500 or 2 to the 1,000 points in this distribution. Okay. So this kind of setting of not knowing exactly what our distribution is almost always what we want to do. So we're going to ask if you can always build such a thing for a family of distributions. We're going to allow the fuzzy extractor construction to be computationally unlimited. Okay? So as kind of a warm-up to showing that you can't always build fuzzy extractors for a family of distributions, we're going to look at a slightly weaker object. And the reason we're going to do this is that the way fuzzy extractors are normally built is that they do two things. The first is that in the generate algorithm, they use a standard randomness extractor to get this key. Okay? And this is also run in reproduce. And the main thing you're trying to do is you need to provide the correct input to the randomness extractor. So there's something called a secure sketch that performs something called information reconciliation. If you haven't heard the terms privacy amplification and information reconciliation, don't worry about them. But what it does is it produces this public value P that along with W1 gets W0 back. And the whole goal of this secure sketch is that P shouldn't have a lot of information about W0. Should only have enough information to get it back from a nearby W1. Okay. So we're first going to show that it might be impossible to build this for a family of distributions, and that'll provide intuition for how it works for general fuzzy extractors. But I should say almost all fuzzy extractors are built this way. Okay. So let's look at how a secure sketch would work for a family of distributions. So when I'm actually creating the algorithms, the only thing I see is my input point, W0. I may have a guess for what other points in the distribution exist, but the only thing I actually see is W0. So the thing I know is I know by my correctness condition that if I'm given a nearby W1, I have to get this point back, okay? At least with good probability. So I don't know what these other points are out here. It could be these points, but I do know that for anything nearby, I have to get this point back, okay? So this correctness condition of mapping back here has to be true whether these are the correct points, these are the correct points, or these are the correct points, okay? And, right, if we have a family of distributions that all intersect at W0 but have all these different points, any of these points could be true, and I don't know anything about them. Okay. So we need to recover from this new value W1, regardless of which distribution the original W0 came from. Okay. And that's just because of correctness. Now, what a good fuzzy extractor algorithm is going to do is to provide security. This isn't going to be the only ball where we have kind of this decoding to the center. The algorithm is going to create other points in the metric space where everything nearby maps to the center of this ball. And the reason it's going to do that is these provide other candidates for the value of W0, which is necessary to hide the value of W0 from Eve. So what a good sketch algorithm is going to do is it's going to tile this metric space with as many of these points as possible. And it seems like it's done a really good job here. There's a lot of points of this distribution which lie at the center of these balls. Okay. The issue with this is now, I didn't actually know what these other points of the distribution were. So if I look at one of those alternate distributions I showed you, those points are no longer at the center of balls. Okay? The only point that's at a center of one of these balls is the actual point W0 that was used in generate. And no matter which distribution W0 came from, it's going to lie at the center of one of these balls. Okay? So this is kind of the core of this impossibility result, is that few points from each distribution in the family are going to lie at the center of the ball. But we know that the true sketched point is always going to be at the center of a ball. So we can just look at, as an adversary, if we know the exact distribution, we can look at the intersection of the exact distribution with the points that lie at the center of these balls. So what this allows us to show is that there's actually a family of distributions that have linear fuzzy min entropy such that any secure sketch construction that has to handle a linear error rate retains only 2 bits of entropy. This is bad. And this is only having to be correct 50% of the time. So this is a really bad impossibility result. And the crux of the main technical result is that we need to build a family of distributions where each distribution has high fuzzy min entropy, and they actually share very few points. Okay. But you might be saying, we don't need to build a secure sketch. We can do something, in fact, entirely different, and maybe a lot more clever than what this secure sketch construction looks like. So I'm going to provide a brief summary of how you might provide an impossibility for a general fuzzy extractor. So let's consider a fuzzy extractor that just outputs a 1-bit key, R. So again, we have our lovely metric space here, and what the reproduce algorithm does is it partitions this metric space into values W1 where reproduce outputs the key 0, and where reproduce outputs the key 1. Okay? And furthermore, the adversary, knowing this public value P, knows this partition. Right? They can see this partition. Okay. So here, the point is that our value W0 could not have lived near the boundary of this partition. If our point W0 lived near the boundary, what we would have is we'd have a circle that lives near the boundary, and all these points in red would not give us the correct key anymore. Okay? So what this allows us to do is to say that we can actually rule out everything close to the boundary as a possible input W0. And for this metric space that I've drawn, and this is just because of correctness, for this metric space I've drawn, this doesn't look too bad. But you can actually show that for high-dimensional metric spaces, in particular for the high-dimensional Hamming metric, almost everything lives near the boundary. And so this doesn't look like a small fraction of the space, it looks like almost everything. And so what that lets us do is, combined with the knowledge of the distribution, the fact that so many points are ruled out by being close to a boundary allows us to leave very few possible guesses for the value W0. So here we get a slightly weaker result, which says that there's a family of distributions that have linear fuzzy min entropy that we again handle a linear error rate. You can't get a 3-bit key out. I should note one caveat here is that we have this condition that we have to be 100% correct on our previous previous result, we only needed about 50% correctness. So this is our second main result. We have a third variant, which is building off a result of Hollenstein and Renner from about 10 years ago, who showed the impossibility of key agreement from bit fixing sources. So we actually get a similar result to our previous theorem, but we can remove this requirement for 100% correctness at the cost of slightly worse parameters that are hidden by asymptotics. So the requirement for, or the quality of the sources goes down, and they have to support a higher error rate. Okay. So what we show in this talk is a new and necessary notion for deriving keys from noisy sources that we call fuzzy min entropy. It measures the maximum probability ball in the metric space, and it just measures the adversary's kind of ideal success, right? If we give them oracle access to the functionality we've provided. This is sufficient with computational security if you believe in obfuscation, which, right, it's an assumption. It's sufficient if the distribution is known, though our construction here for information theoretic is very much not a polynomial time construction. And it's insufficient if you don't know what the distribution looks like. And this is in contrast to the randomness extractor setting, where you don't have to know the distribution and you're still able to do the task of key derivation. And this is a big difference between the two settings. We have several variants of this insufficiency setting, both for secure sketches and fuzzy extractors. And the question that I'll leave with is, it seems like this is kind of guiding us that computational security is the right thing for fuzzy extractors. But right now, the construction that we have requires a very strong assumption. We want to ask, can you provide computational fuzzy extractors for sources with fuzzy min entropy based on something that's a little bit weaker than general obfuscation? With that, I'll stop and take questions.
So, any questions? The next speaker could already come forward.
Great talk. So it seems in your theorem, basically your attempt is work on you find a specific family of distribution, then you can break it in whatever sense. But what if we always work on the largest possible family, which is essentially any possible distribution with certain entropy? Yep. Is your impossibility result still apply there?
So the short answer is no. It is worth saying that, right, the fully uniform distribution, there's no like family of distributions, right? Because it.
For example, like we just define the largest possible family, right? But the distribution with certain entropy low bound.
Okay, so our proof does not extend to that setting, but I think the problem's still there. And the problem is, at least for secure sketches, I'm not sure about fuzzy extractors. The problem is just you're setting points to be distinguished based on being at the center of the ball. And you're choosing those points without knowing what the rest of the distribution looks like. And so the fact that we have to build a construction for a particular family where we can show distributions don't overlap very often, but it may be a weaker result, but I think you can extend it for essentially any distribution or any family. But we haven't done it.
Okay. Can I ask one more question?
Actually, we have a bit of time to catch up from the session before, so I suggest that further questions are taken offline. And thanks again for a great talk.